Hey everybody. Um, so we're going to look at graphing a rational function today. So I've got this example that I'm going to do here. And the big idea with graphing rational functions, excuse me, is we're going to collect a bunch of information and then we're going to use that information to put our graph together, right? And the purpose behind this, right? We all know that we can graph things with computers, but it helps us build our intuitions around functions. And if we don't have good intuitions when we're working with them, we're not just doing mechanical operations on them. Um, it's difficult to understand things well if you haven't gone through processes like this. So um, there's a few things we're typically going to look for that I'll list here, and then we'll get started on it. We'll often want to find the domain. Remember, the domain of our rational functions is always going to be all values of x except for the values that make our denominator equal to 0. So we'll have to find out what those are. We're going to look for our intercepts, right? And these are things that most functions that we graph, we look for this kind of stuff. Right? We usually, for our typical functions, we often know the domain. Things like lines and parabolas, we know are all real numbers. Square roots, we look for where it's the argument is positive, things like that, or non-negative, I should say. Intercepts are often convenient. They're great to give us some anchor points. We know our function goes through this point. But then a couple of things that are particular to rational functions, not that no other functions have these, but these are not as common. We're going to look for our horizontal asymptotes, right? These are horizontal lines that the function, we sometimes say, approaches as x goes towards infinity or x goes towards negative infinity. A good way to think about that at this point is that our function begins to look like that line once we get far away from 0. Near 0, these rational functions can look a bit bonkers, but out at the edges, they often start to look like something. Well, they always will start to look like either a line or some polynomial. So we'll look for these horizontal asymptotes or slant asymptotes. These are not the only two possibilities with rational functions, but these are the ones we're focusing on at this point. And so these are the only ones we'll actually look at. There's horizontal asymptotes or slant asymptotes. And then we're going to look for our vertical asymptotes and our holes. These are the removable discontinuities. And I really should maybe have thought about listing this in a different order, because the domain and these vertical asymptotes or holes are linked. That these holes and vertical asymptotes will appear at the same places that our denominator is 0. Okay, and so and on the topic of the order that I wrote things down, there's no special order here. These don't have to be done in this order. I just wrote these down. I'm going to throw one more thing in here. I'm just going to put in, let's say, test points. And all I mean by this is sometimes when we collect this information, it might not be 100% clear what the function looks like. And so we might just plot a couple of extra points to help us understand something, or maybe apply, let's say, some reasoning, like trying to figure out where it's positive, where it's negative, right? So if you know, for instance, the function is approaching 0, if its horizontal asymptote is at 0, well, is it positive or negative as it gets closer and closer to the line y equals 0? And so you can sometimes do that with simple reasoning, say everything is squared or a positive number, it's going to be positive, or maybe you do it by testing a point and seeing what happens. So we'll talk more about that. So let's dive in. The first thing I'm going to do, and like I said, the order doesn't necessarily matter. I'm going to factor this thing. I know that eventually I'm going to want it factored. Both forms, this where it's written out as these expanded polynomials, this is a useful form, but so is the factored form. So I'm just going to get that part out of the way, and I'm going to do the numerator and the denominator separately. So let's look at the numerator first. This is 2x cubed minus 4x squared minus 16x. I can factor out a 2x. All right, that's the most obvious one I see. What will be left? We've got an x squared minus 2x minus 8. And then this can be factored as, let's see, we're going to have the factors of 8. We need of negative 8. We need them to add up to negative 2. So it looks like we'll have a negative 4 and a positive 2. So if that was fast, you might want to brush up on factoring. You can always double check this, expand this, and you'll see that we get back what we started with. So there's our numerator. Let's do the denominator. The denominator is x cubed plus x squared minus 4x minus 4. And here I'm noticing that there's not a common factor to all 4 of these terms, so I can't use the trick I used above. But I noticed the first 2 terms both have an x squared in them. So this, I'm factoring this term first, or these 2 terms first, and I get x plus 1 left behind. And then these second 2 terms both have a negative 4 in them. So let's factor out that negative 4, and we're left with x plus 1. Again, if that is at all mysterious, try expanding this and see that we get what we started with. Now I've got a common factor of x plus 1 in both terms, right? I've got 2 terms. I've got the x squared times x plus 1 and minus 4 times x plus 1. And so I can factor out that x plus 1 just like we factor out the 2x up above when we've got a common factor, and in this case, that common factor is x plus 1. And what's left in this first term is an x squared, and I've got an x minus 4 there. I recognize that x squared minus 4 is the difference of squares, and so I can factor this as x minus 2, x plus 2. All right, so there is my denominator. And so now I have, let's just put this up here. I've got this Rx, our function R of x is equal to, here's my numerator, 2x times x minus 4 times x plus 2. And then times x plus 1, x minus 2, x plus 2. Okay. So there is the nice, I've got 2 forms of my function now. So I'm just gonna copy these. I'm gonna take my list with us too, so we can just keep going on it. Give us a new page. All right, let's get ourselves some more space. Try to keep this nice and spaced out. Just put it here. Okay, so let's now go through some of these pieces of the puzzle. So let's go ahead and start with the domain. And so the domain is anywhere where the denominator is 0. Sorry, the domain is everywhere except where the denominator is 0. So we go looking for where the denominator is 0. In other words, I want to know when is x plus 1 times x minus 2 times x plus 2 equal to 0, right? So this is one of the big reasons we factor, that we can see these zeros easily. So that means it's going to be 0 if x plus 1 is 0, if x minus 2 is 0, or x plus 2 is 0, right? And of course, these are easily solved. So this is true if x is equal to -1, or x is equal to 2, or x is equal to -2. So our domain is going to be all real numbers except x equal -1, -2, or 2. Okay, so often we will just write x is not equal to -1, -2, or 2, implying everything else but that. I made it a little more explicit here. All right, so there's our domain. And so whenever I get a piece of information, right, this is a long process to graph this. I typically will just give it a little box so that later, when I've collected all the information I need and I'm going back trying to put it all together, I don't have to search too hard to find it. There's a nice piece of information for me right there. So let's look now, since I said these are connected to the vertical asymptotes and holes, let's use this information to get our vertical asymptotes. So here's the big idea. We're not going to go into a ton of detail. We've discussed this elsewhere, but whenever there's a zero in the denominator and that zero does not appear in the numerator, we get an asymptote, right? And what's happening is behavior very similar to 1 over x. When that thing in the denominator gets incredibly small, the fraction gets incredibly large, right? So the denominator is tiny, the fraction gets large. So that's when we get these vertical asymptotes. However, if there happens to be the same zero in the numerator, then it means the denominator is getting super small, but so is the numerator, and it sort of cancels that explosive behavior, okay? So we look for places where when we have a zero in the denominator that we don't have in the numerator, we get a vertical asymptote. So for us, we have two vertical asymptotes. At y equals -1, sorry, x equals -1. So we have the line x equals -1 is one asymptote, and x equals 2 is our other asymptote. We don't have a vertical asymptote at x equals -2, because you'll notice the factor x plus 2, this is the factor that's 0 when x equals -2, appears in both the numerator and the denominator. And what we get instead is a hole at x equals -2. Right? And if we want to know exactly where that hole is, we can look at this expression, this factored expression, and cancel the factors of x plus 2. Now, I've written an equal sign here, but this is not technically true. I need a little, let's put a little asterisk here and say, these two things are equal except when x equals -2. Because the expression here is not evaluatable, cannot be evaluated at x equals -2, but this one can. Okay? And if I want to know where that hole is, I can look at this new expression, the one that's the same except at x equals -2, and simply evaluate it at x equals -2. So I'm gonna call this thing r star, right? For it's like almost r except for at this one point, and evaluate it at -2. So I'm putting -2 in where x appears there. So I've got 2 times -2, -2 minus 4 over -2 plus 1, -2 minus 2. So what do we get? We get a -4. Just going to go with parentheses. -4 times -6 in the numerator. In the denominator, I've got -1 times -4, and all of this works out to be 6. So that means I can say even more specifically up here. Let's, in fact, say this leads us to the hole is not just the x value, but we know exactly where that hole is. Right? And so this is a nice point for us to have, because even though this is not actually a point on the graph of our function, we know that our function is going to go right up to that point and then carry on. Right? That's one of the features about these rational functions. So when we have a hole like this, it tells us a lot about our graph, even though technically it's not part of the graph. We know what the graph must do nearby it. It has to go right through that hole. Okay, so we've got our domain and our vertical asymptotes. Let's go to our horizontal asymptotes. And in this case, I don't need to worry about slant asymptotes. We have a series of rules we compare the degree of the numerator to the degree of the denominator in the case where they have the same degree. And in this case, the degree of the numerator is equal to 3, which is also equal to the degree of the denominator. Okay, they're both cubic polynomials. When this is the case, the horizontal asymptote is simply the ratio of the coefficients, right? There's secretly a 1 in front of that x cubed. And so we just look at the ratio of 2 to 1, or 2. So the line y equals 2 is going to be our horizontal asymptotes. Okay. All right. So let's, excuse me. Let's sketch a little graph. So I'll make us some axes. There we go. And let's grab our relevant information. So let's get our vertical asymptotes and our hole. Copy that and paste. All right, let's get our horizontal asymptote. Whoops. There we go. And what other information do we need? Oh, sorry, we skipped the intercepts. Well, we'll do those, and then we'll jump down to where I started doing that. So one more piece of information we want to get is our intercepts. So let's do that here. Take our last little quadrant of this screen. So the intercepts, remember, we're going to get our y-intercept. We simply look at where is r, what is the value of r, our function at 0. For this, the expanded form of the rational is usually easier, right? I just put in zeros for all the x's. So 2x cubed is 0, minus 4x, that's 0, minus 16x. So I got to end up with a 0 in the numerator. And in the denominator, I end up with a -4. So 0 over -4 is 0. So this gives me the point 0, 0 as my y-intercept. And that turns out to also be the x-intercept, one of the x-intercepts. So let's find the other x-intercepts. So for the x-intercepts, we're going to look for where is r of x equal to 0. So here, the factored form is really nice. This 2x times x minus 4 times x plus 2, or x plus 1, x minus 2, x plus 2. We want to know where this thing is equal to 0. Okay. Well, when's a fraction equal to 0? Is when its numerator is 0 and its denominator isn't. Okay. If they're both 0, it's undefined. But if the numerator is 0 and the denominator isn't, then the whole fraction is equal to 0. So this numerator is 0 if 2x equals 0 or x minus 4 equals 0, right? Our nice factors. We don't care about this factor because when it's 0, the denominator is also 0. So the numerator is 0 when 2x is 0 or x minus 4 is 0, or this means x equals 0 or x equals 4. So we get the points 0, 0, which we already got because that's our y-intercept, and we also have the point 4, 0. Okay, now let's go down with all this information. So I've got our intercepts. Whoa, I don't know what I just pressed. We've got our intercepts. We've got our domain and our asymptotes and holes associated with that domain. We've got our horizontal asymptotes, and we have our intercepts. So I'll write those intercepts here. So let's arrange this a little prettier. There's all our asymptotes, vertical and horizontal. We've got intercepts at 0, 0, and 4, 0. And I think that's all the information we have right now. If we figured out that we forgot something, we'll just go back and get it. So let's put a couple of these things in. So I'm going to start with the points I know. I've got a point at 0, 0. And I'm thinking a little bit about my vertical asymptotes. I want to leave space for everything. So let's put our 0.40 out here. I'm going to put that hole in. I'll put that in a different color because it's not actually a point on the graph. So -2.6 should be something like that maybe. And I'm going to sketch in my asymptotes. Let's do them in this blue. I'll make it a little thinner of a line so they don't get too, it's not too cluttering. So there's a line, there's a vertical asymptote at x equals -1. So right here ish, and one at x equals 2. Looks about right. And then we have a horizontal asymptote at y equals 2. So somewhere about right here. Okay. So now we want to figure out what this graph looks like exactly. So we're going to use a bit of logic here. So for parts of it. So let's start here. We've got, so all right, sorry, I'm stumbling over my words. Let me start this over again. We're going to use a little piece of logic that we haven't talked about yet about the continuity of these rational functions. So rational functions are continuous on their domain. What this means is, except for that hole and those two vertical asymptotes, everywhere else, our function is continuous. Continuous, for our purposes, is simply going to mean that you can draw it without picking up your pen. So for this function, what it means is, on each of these sections, there's a section to the right. Here, let's put in these lines. This is the line x equals 2. This is x equals -1. This is the point -2.6. We've divided up the coordinate plane into several sections. Everything to the right of x equals 2, everything between x equals 2 and x equals -1, everything between x equals -1 and that dot at -2, and then everything below that point at -2.6, right? In each of those regions, I should be able to draw my function without picking the pen up, right? It won't have any jumps or anything like that. At those lines, for instance, as we cross over from above x equals 2 to below x equals 2, I will have to pick my pen up because the graph does not go through that line. That continuity tells us something important. For instance, let's do a little here. Let's say here's a piece of a graph. Here's the x-axis. If a graph is positive over here and negative over here, and it's continuous, meaning as I draw my graph from the first dot to the second dot, if it's continuous, there's no way I can get to this other point without passing through 0. Okay? So if our function switches from positive to negative, we know that it must pass through 0. Or we must have one of these places where we pick up our pen. So for instance, if I have, let's erase this one. The only other way we could go from positive to negative is if I had like an asymptote, and my function does something like this. It goes in that direction over there and goes down to infinity over there, to negative infinity over there, right? Because I've picked up my pen, then we can switch. So the only way we can switch from positive to negative is if there's a 0 we know about, if there's a 0, or if there is an asymptote or some kind of jump discontinuity, but we don't have those. So I guess if we had a hole right on the x-axis, then we could end up with a place where at that hole we switch from positive to negative. This is a big deal, and let me show you why. Let's look at the region greater than x equals -2. What do I know about my function? I know that because we have this horizontal asymptote at this is y equals 2, that I know as x gets larger and larger, my graph gets closer and closer and closer to that line. Okay. All right, I'm going to grab the copy of our function and bring it down here too. We need to say a couple of things about this. Have this down here. All right. Just put it here. We'll erase that extraneous stuff. Okay, sorry about that. So we've got this 0 at 4, 0, and we know that the graph is getting closer and closer to that line y equals 2. We don't know for certain that it doesn't go over it and then back towards it, but we're not going to worry about those kind of details. We're just doing a sketch right now. One other piece of information we have is that this 0 at 4, 0 came from this factor. Just like with polynomials, the multiplicity of that factor tells me how the graph passes through. And because the multiplicity is 1, it passes through like a line. In other words, it doesn't bounce off like a parabola might. It continues through and gets to the other side. Okay, whenever we have a linear factor that's causing a 0, it's going to go right through like that. Okay, now because it's negative below 4, right? Notice that once we get past that point where our x values are below 4, we know it has to stay negative all the way, and it can't jump back to positive before this asymptote at x equals 2. Because if it did, right, if it did somehow go back to positive, there would be another 0. But we found all those zeros, and there isn't one. It would have to pass through, but it doesn't. So that tells me it has to stay negative, and we know that it's going to then go down towards negative infinity as it approaches that asymptote at y equals 2. Okay. So there's one region. Let's look at the region between x equals -1 and let's look below x equals -1. We've got a hole in our graph. So one thing I know is that my graph just passes through this hole. There's a hole there, and it goes through it, right? I know it must be going the way I drew it because this hole is in a positive region, and I know the graph is going to be near it, so it's going to be positive. And there's no more zeros, so there's no way for me to go negative. So I can't do something like this. I can't have this asymptote where I go down to negative infinity because I would have to pass through 0. So I know that as I approach this asymptote, I must be going up to positive infinity. And then I know as my x values get smaller and smaller, I've got the horizontal asymptote. It's approaching y equals 2 in that direction. So I've got the outside of my function done. Inside, what do I know? I've got a 0 here at 0, 0. What I don't know is I know that the 0 comes from this factor, which is linear. So it has multiplicity 1. So I know it's passing through this graph like a line, right? It might be going like this. It might be going like this. I don't know which one of those it's doing. So how can I figure that out? Well, an easy way to do it is to use a test point. I pick a convenient point on either side of this. So I want to pick a point between -1 and 0 or 0 and 2 and see whether my graph is positive or negative. I'm going to pick a point. I'm going to pick an x value between 0 and 2 because there's a nice easy one in there, r of 1, x equals 1. And let's just evaluate r of 1. Right? And this is easy enough to do. I'll just use this expanded form. I'm going to have 2 minus 4 minus 16. In the numerator, I'm going to have 1 plus 1 minus 4 minus 4. And this is going to give me what? I'm going to get -2, -18, and -6, or +3. Okay. Which means, so let's put this point in, 1, 3, the point about right here. Now I know not exactly what the graph looks, but I know good enough what the graph looks like. It's positive. I know that it must go through that 0 down there. And because it's positive over here, it has to go off to positive infinity toward that asymptote, because if it went towards that negative infinity at that asymptote, it would have to pass through 0 again. And we know there's no more zeros. Because we have a linear factor, I know it passes right through that 0, and it must continue on down like this. And so I get a sketch of what this graph looks like, right? So this is obviously a bit messy. It's not a perfect graph of this function, but it tells us a lot about its behavior. We know certain things that happen to it, right? We know that as it approaches x equals -1 from below, it's exploding to infinity. And that as it approaches, say, x equals 2 from above, it explodes to negative infinity, right? We can make all these kinds of assessments of its behavior based on this sketch. Not to mention, we did some good work in finding all the information that got us this. So let's finish up by just looking at a prettier graph of this. Let me share a computer version of this. So here's our function. Let's put in some of those points. There's the hole. The computer doesn't actually show the hole, so I have to put that in manually. Here are our asymptotes, and here's I put in the vertical and horizontal asymptotes, and so we can see we got a pretty decent sketch of this function. You can see out towards infinity, all this craziness in the middle kind of disappears, and we have something that looks very much like the line y equals 2. It doesn't look exactly like the line y equals 2. It's always going to be a little bit different, but it looks very similar to it. The differences are negligible. Okay, that is it for this one. Thanks, everybody. I will see you next time.